In this video, we'll investigate the limit of a sequence. Up first, we'll just look at an intuitive definition. A sequence a sub n has the limit L, or we can write that as the limit as n approaches infinity of the sequence equals L. We could also think of that as a sub n approaches L as n approaches infinity. Let's look at a graph to help us visualize what's happening here. Let's say that this vertical axis represents a sub n and the horizontal will be n, and then we'll have some terms in that sequence. We'll have a sub n, let's say it's down here, a sub 2, let's say it's going up here, a sub 3, and so on, and it's doing this kind of thing. It's approaching a certain value. Let's call it L, the limit. In this case, we would say that this is a convergent sequence. It converges because as n gets big, the terms of that sequence start to approach that value L. We could also see another example. This time, let's say the a values are doing something like this, and they're not converging to a value like L. Here, the a values are getting bigger and bigger and bigger. In this example, this would be a divergent sequence. Those values are just continuing to get bigger. They're not converging to a specific value like we see in this example, where it again is convergent. A more precise definition of a limit of a sequence is given here. Here, if for every epsilon greater than 0, there is a corresponding integer capital N such that little n is bigger than capital N, then the absolute value of a sub n minus L is less than epsilon. You may recognize some of that notation from our limit definitions earlier. We will again look at a visual to kind of help us see what's happening. Again, the vertical is a sub n, horizontal is our n values, and we want to approach an L value if this is a convergent sequence. Let's say we have a horizontal line up here and a horizontal line down here, and this upper one we'll call y equals L plus epsilon, and the lower one will be y equals L minus epsilon. We have this epsilon window around our limit. Then if we want this to be a convergent sequence, the a sub n values may look something like this. Eventually they will start to remain within those two horizontal lines with the epsilon window around our limit. So this picture will be valid no matter how small epsilon is chosen. Usually a smaller epsilon will be required for a bigger n value. So if n is here, it starts to fit within the window, but if we chose an n value down here, notice not all of them fall within these horizontal lines within that epsilon window. So if epsilon is rather small, if we have a tiny window around our limit, then we'll need our n values to be much bigger. Next, we'll look at some examples and determine whether the sequence converges or diverges. If it is a convergence sequence, we need to actually find the limit. We're going to use a familiar trick that we used back when we were calculating limits in previous sections, which is to divide the numerator and denominator by the highest power of n that occurs in the denominator. So we'll have the denominator n plus 3, recognize the highest power of n is n. So we're going to divide the top and bottom by n. This will give us 5 divided by n divided by 1 plus 3 divided by n. And now let's think of that as a limit. The limit as n gets really big of 5 divided by n divided by 1 plus 3 over n gives us the numerator is approaching 0. The denominator is approaching 1 plus 0. 0 divided by 1 is 0. So this is a convergent sequence. It converges to 0. The limit as n approaches infinity of a sub n being this piece, is 0. So we have a convergent sequence. In part B, notice we don't have a fraction, we just have the radical. We can just think of the limit as n approaches infinity of 5 square root n plus 2. If n is approaching infinity, we're getting a really big number under the radical. The square root of a really big number is still a really big number, so we're approaching infinity. This example diverges. This is a divergent sequence. In the next example, let's again think of this as a limit, and we can divide by the highest power of n that occurs in the denominator. So we'll take the limit of cosine, divide the top by highest power that occurs in the denominator is n. So that is n pi divided by n divided by n plus 1 divided by n. Limit n approaches infinity. In the numerator of the cosine function, we get pi. In the denominator, we get 1 plus 1 over n. Here, we have n getting really big, so this fraction goes away to 0. So we have pi divided by 1, which is the cosine of pi, which is -1. So this is a convergent sequence. This one converges, and the limit as n approaches infinity of cosine of n pi divided by n plus 1 converges to -1. In our final example, we again want to think of this as a limit, and we're going to let n get really big and divide the top and the bottom by the highest power of n that occurs in the denominator. So we have to be careful with this one. In the denominator, we have the square root of n cubed plus 4n. We're going to divide that by the square root of n cubed. So in the numerator, we are also dividing by square root of n cubed. Continuing to simplify this, we'll get in the numerator n squared divided by the square root of n cubed. That will simplify to the square root of n. And in the denominator, let's push this square root of n cubed under this other radical. That will give us the square root of 1 plus 4 divided by n squared. And now evaluating the limit as n gets really big, In the numerator, we have the square root of n. So as n gets really big, the square root of a really big number is, again, a really big number. So we have infinity, basically, divided by 1 plus, again, if n is getting big, this fraction is 0. So we have the square root of 1 plus 0. We're getting infinity, which means that this sequence diverges.